Welcome to day 52. Have you ever seen a small team build an amazing AI feature and wondered, how did they do that without a massive budget? Well, the answer is often a clever technique that lets them build on the work of others. Today, we're talking about transfer learning. Anyone who's tried to train a neural network from scratch knows the pain. You have a great idea, but actually getting a working model, it's just full of hurdles. So why is it so hard? By the end of this, you'll understand a really powerful way around this entire problem. First up, there's the data. I mean, to learn anything useful from a blank slate, a model needs to see a ton of examples. For most real-world problems, getting and labeling that much data just isn't practical. Then you've got the resource problem. Training a big model can take days or even weeks, running on some seriously powerful hardware. That kind of compute power is, well, it's expensive, and it's a huge barrier for a lot of people. And finally, there's just the sheer amount of time it all takes. The whole process from getting the data to finishing the training can stretch on for months. So you've got these three big challenges: data, cost, and time. They make starting from scratch a monumental effort. But what if you didn't have to start from scratch? Right, the traditional way forces a model to learn absolutely everything on its own, from the simplest of patterns to the most complex ideas. We're going to talk about a much, much smarter approach. And that approach is called transfer learning. The core idea is incredibly simple. Instead of building a model from the ground up, you take a model that's already been trained on a huge general dataset and you just adapt its knowledge to your new specific problem.
Okay, here is the best way to get the intuition for this. Imagine you already know how to code in Python, and now you need to learn JavaScript. You don't go back and relearn the basic concepts of what a variable is or what a for loop does. You already have that fundamental knowledge. You just transfer it over and learn the new syntax. Transfer learning is doing exactly that for models.
So let's really contrast these two approaches. Training from scratch, that's like building a skyscraper by going to the quarry yourself and mining the stone for the foundation. It's a massive, massive job. Training from transfer learning, on the other hand, is like getting handed the keys to a 90-story building that's already built. All you have to do is customize the penthouse suite for your company. You're just leveraging a huge amount of work that's already been done. And this approach directly solves those big three problems we started with. First, it's way more efficient. You can train models with less data and in less time. Second, it's more accessible. You don't need a huge budget for compute clusters. And third, you often get better performance because you're starting with a model that already has a solid fundamental understanding of the world. All right, so the intuition makes sense, but how does this knowledge transfer actually happen? Let's take a look under the hood. The whole process really boils down to three main steps. First, you pick a good pre-trained model, one that was trained on a big general data set that's related to your problem. Then you configure that model for your new specific task. And finally, you train it a bit more, but this time only on your own much smaller data set. Now that second step, configuring the model, that's where the real secret sauce is. This is where you make the critical decisions about what knowledge to keep and how to adapt the model for its new purpose. This usually involves three key moves. First, you freeze the early layers of the network. These are the layers that have learned to detect really basic things like edges, colors, and textures. That knowledge is almost always useful, so you lock it in place. Next, you remove the very last layer of the original model, because that part is way too specialized for its original task. And finally, you add your own brand new trainable layers at the end. These new layers are the only part that will learn from your specific data. Now, in the academic worlds, you might run into a few formal terms for this. There's inductive transfer, where you have the same domain but a different task, like using a cat identifier to learn how to identify dogs. Then there's transductive transfer, with a different domain but the same task, like using a model trained on photos to analyze paintings. The names aren't that important. Just know they're all different flavors of the same core idea. So where do we actually see this being used? Well, the short answer is pretty much everywhere that machine learning is used today. It is the standard operating procedure in computer vision for things like object detection. It's absolutely fundamental to modern NLP for tasks like sentiment analysis. It's used in supercritical areas like medical imaging to help diagnose diseases. And really, it's the very basis for how we customize today's large generative AI models for specific uses. Let me give you a really concrete example. You can download a model that's been pre-trained on the giant ImageNet dataset so it knows what cats, dogs, and cars look like. Then, with a pretty small dataset of your own, you can fine-tune that powerful model to become an expert at spotting tiny, specific defects on a manufacturing line. You're leveraging billions of calculations that somebody else already ran. So, if you boil all of this down to just one central idea, it's this. Transfer learning is about standing on the shoulders of giants. It lets you take the incredible amount of knowledge that's already been captured in a pre-trained model and apply it to solve your own problems, much more quickly and effectively. So the next time you're starting a machine learning project, don't just ask, how do I build a model from scratch? Instead, ask yourself, what existing knowledge is already out there that my project could borrow?